In the previous video, I have briefly mentioned the two main equations that are used by students in chemical energetics. And then I went through how we can derive the first equation. If you are given heat of formation, why is it heat of formation of products minus the heat of formation of reactants? So if you do need to find out why this is so, please go and take a look at my first video. For the second video, I will focus on the derivation for heat of combustion. As in, if you are given heat of combustion, how do we know that it is combustion of reactants minus combustion of products? Right, because sometimes when we memorize, we might get the order mixed up. So let's move to the second equation. Let's say we have this as this equation: carbon, hydrogen, oxygen forming ethanol. In general, this is our heat of reaction. This is the reaction that we are interested in. Right, some of you who are alert, you might recognize this to be heat of formation of ethanol. Right, but no matter, in general, this is a heat of reaction. So what is the enthalpy change going from left to right? What happens if you are given heat of combustion information? How do we fit it in a cycle? First of all, a quick recap on the definition of heat of combustion. Enthalpy change when 1 mole of pure substance is completely burned in oxygen. So what happens when we burn all these individual substances in oxygen? We get carbon dioxide, hydrogen, we get water. Oxygen doesn't really combust, so right, we do not have a compound for combustion of oxygen. Same thing, when you combust ethanol, you will get carbon dioxide and water. So this is our products for combustion. Where do we draw the arrow if you were to form a cycle? If you look at the definition again, 1 mole of pure compound is completely burnt. So we start off from here, and then we draw towards the substances that are formed. We form carbon dioxide, we form water. So in this direction is the heat of combustion. For carbon combustion, we have 1 mole, so this is the heat of combustion for carbon. Hydrogen, you have 3 moles, pointing towards the products. 3 times heat of combustion of hydrogen gas. Again, oxygen, there's no heat of combustion. Now we move on to the ethanol side. Combusting ethanol to carbon dioxide and water. We point from ethanol to carbon dioxide and water. 1 mole of ethanol combusts. This is the heat of combustion of ethanol. So we have formed a cycle. Let's try to use Hess's law to form an equation. The convenient way to do it is we compare the clockwise direction and equate it to the clockwise direction, or the arrows that are going into the clockwise, anti-clockwise direction. So we start off with this corner, and if we follow the flow, the heat of reaction and the combustion of ethanol flows in the clockwise direction. For the anti-clockwise direction, we start off again from the same spot. It will be these two values here. So we equate the clockwise direction to the anti-clockwise direction. We have heat of reaction and combustion of ethanol on the same side. We have combustion of carbon and combustion of hydrogen on the other end of the equation, on the opposite side. And as a subject, or to make the heat of reaction the subject, we take the heat of ethanol and bring it over to the other side of the equation. So we subtract combustion of ethanol. So you can realize by now, heat of combustion of reactants minus heat of combustion of your products. That will give us the heat of reaction. Right. Why will this work? Because you realize the flow of the arrows. Your heat of reaction will always end up as the same side on the equation as the heat of combustion of your products. They will end up on the same side. So when we bring it over to make heat of reaction the subject, you'll be subtracting heat of combustion of your reactants. Or rather, you'll be subtracting the heat of combustion of your products.